Hello everybody, I just wanted to add one last note before we started going into some worked examples of the Lagrangian. So if you'll recall, the Lagrangian is T minus potential energy, but notice that this does not account for forces that are not arising from a potential. Such a situation occurs when frictional forces are present. So in this case, what do? Well, Lagrange's equations become d over dt partial L over partial Q dot K minus partial L over partial QK equals capital Q K, where Q sub K represents the forces not arising from a potential. So frictional forces are sometimes proportional to velocity. So we would have, like, for example, F friction equals minus K times V. Frictional forces of this type can be derived in terms of a function F. It's a fancy kind of F, and it's known as Rayleigh's dissipation function. So F equals 1/2 the sums of K V squared over all the particles in the system. From this definition, it's pretty clear that this frictional force right here, this is just minus the partial derivative of Rayleigh's dissipation function. I'll write it nice and curly to make it look very different from force. With respect to velocity, which we can represent symbolically as just saying, oh, this is the gradient with respect to velocity of Rayleigh's dissipation function. So the work done by the system against friction is going to be dW equals minus F sub F times, or well, rather the dot product with the radius differential. And this should be a definition that we're pretty clear with from elementary mechanics. It's just a definition of work, and we have this minus sign here because, well, we're doing the work by the system against friction. So this is basically equivalent to saying, well, we have the force of friction, dot product with the velocity vector, and then dt, which is just going to be k. It's just going to be minus kv squared dt. So when you integrate over both sides, right here and right here, it becomes pretty clear that the rate of energy dissipation due to friction is twice the Rayleigh dissipation function. So W due to friction is twice the Rayleigh dissipation function. The component of the resulting generalized force, Q sub K, is given by the sum of these forces on each of the particles times the partial derivative of the radii with respect to Q sub K. And as we saw right here, another way of saying that is minus sigma gradient V times partial Ri partial QK. And partial Ri partial QK, well, partial QK, we can just put a dot over that. We could just take the time derivative of both sides of this. Basically, the reason I'm doing that is to show this qk right here, well, that's just equivalent to minus the derivative of Rayleigh's dissipation function with respect to the time derivative of the generalized coordinate question. So with this, I'll make some space right here. With this, we're going to get the Lagrange equations with dissipation, which are d over dt partial L partial q prime k minus partial L partial qk plus the partial derivative of Rayleigh's dissipation function with respect to q prime k is equal to 0. So we have two scalar functions, the Lagrangian and Rayleigh's dissipation function, which must be specified to obtain the equations of motion.